So by the end of this video, we'll be able to determine whether a system of equations has one solution, no solution, or infinitely many solutions. So when we are solving a system of equations, one of three things will happen. First, we'll see a situation where we have one single solution. And essentially what's happening here is we will actually get a point of intersection. So if you get a point of intersection, you have an actual answer, an actual point where those two linear equations intersect and cross. The other thing that we'll see is we will see a situation where we have no solution, and we'll talk about what that means and what is actually happening there in the upcoming slides. And then the third thing that we'll see is we will see something called infinitely many solutions. And again, we'll talk about that in the upcoming slides as well. But the things you need to remember here are that when we're solving a system of equations, one of these three things will happen. So the best way to be able to denote whether we have a no solution or infinitely many solution situation is to just jump in and give it a try. So here, let's start solving this using elimination since it's already set up into columns. So I'm going to start by picking a variable to eliminate, and I'm just going to pick to eliminate x. Now I notice that this is very close to being ready for elimination, but I need them to have opposite signs. So here I'm going to have 3 be my coefficient, so I need a positive 3 and a negative 3. So I'm going to leave that first equation alone. So I'm going to have 3x plus 2y is equal to 10. That takes care of the 3 for the x. Then I need to multiply this second equation through by a negative 1. So that's going to give me a negative 3x plus a negative 2y is equal to negative 2. So now I'm going to utilize elimination, and I'm going to add these two equations together. So here what's happening is I add them together and I get 0x plus 0y is equal to 8. Now 0x is really 0 and 0y is really 0, so I end up with 0 equals 8. Essentially, my variables are both gone, and I'm left with this statement here. So my variables have both been undone, not by my own doing. I was just trying to eliminate x, but as I tried to eliminate x, they both eliminated. And then from here, I'm left with this statement. And if I look here at this statement, 0 equals 8 is a false statement. So if you are solving a system and you end up with both of your variables eliminating or disappearing, and you're left with a false statement, this is a situation where we have no solution. Now, let's think about what's really happening here and what else we could check to really understand this. So remember, when we're solving a system of equations, we are solving to find where two lines intersect. So here I would have one line, here I would have another, and I'm finding this point. Now, if I have no solution, that means that I have no point of intersection. And if I think about that, I know of lines that have no point of intersection. Those are called parallel lines. So what I expect to see happening is that if this is a no solution problem, I have two lines that are parallel, and I know that parallel lines have the same slope. So there's actually an additional way that we could check for a no solution problem. We could actually take both of these equations and rewrite them and see if they are in fact parallel lines. So let's start with this first one here. If I rewrite this equation, remember to find the slope, we need to put it into slope-intercept form. So I'm going to start by subtracting 3x from each side. So I end up with 2y is equal to 10 plus a negative 3x. Divide both sides by 2. I find y is equal to 5 plus a negative 3 over 2x. So I can clearly see that my slope of this line is negative 3 over 2. Then if I rewrite this second line here, again for y, so I can identify the slope, subtract 3x from each side, I get 2y is equal to 2 plus a negative 3x. divide both sides by 2, y is equal to 1 plus a negative 3 over 2x. Again, I can see I have the same slope. So if you look here at these two equations, we have different y-intercept values, but we have the same slope. Which, remember, same slope means parallel lines, which means the two lines never intersect, which means there's no solution because there's no point of intersection. So if you're looking for a no solution, you can either rewrite them and look to see if they're parallel lines, or you can start to solve the system as normal. The variables will be gone, and you'll be left with this false statement, something like 0 is equal to 8. So example 2 here, again, I need to pick a variable to eliminate. So I'm going to eliminate y here. Now, I notice I have coefficients of 1 and 3, so I need to get common coefficients here. It's like finding a common denominator. So I'm going to pick 3. So I need 1 to be a positive 3 and 1 to be a negative 3. Since this one already has a positive 3, I'm going to leave that second one alone. So just have negative 6x plus 3y is equal to negative 12. And then I need to multiply this first equation through by a negative 3 to get that y to have a negative 3. So negative 3 times negative 2 is a positive 6x. Then I get negative 3 times 1 is a negative 3y is equal to negative 4 times negative 3, which is a positive 12. So now this is set up to work for elimination. So I then add those two equations together, and I end up with 0x plus 0y is equal to 0. So on the left-hand side, I really have 0, and on the right-hand side, I have 0. So essentially what I see here are that my two variables are both gone. They've both been eliminated. And I'm left with this statement here. And I'm left with this true statement of 0 equals 0. And what this is ultimately telling me is that something special is going on. I'm not really quite sure because it's a true statement, not a false statement like the previous one telling me there was no solution. But what I want to do here is I want to explore what's actually happening and then come up with my conclusion. So let's, like the last slide, let's rewrite these so we can see what's happening with these lines. So I'm going to rewrite this first one here so that I can see the equation of a line in slope-intercept form. So I'm going to add 2x to each side. So I end up with y is equal to negative 4 plus 2x. And then I'm going to take this second equation here and rewrite this as well. So here I need to get y alone, so add 6x to each side. Then we have 3y is equal to negative 12 plus 6x. Divide both sides by 3, and I end up with y is equal to negative 4 plus 2x. So if I look here at my equations written in slope-intercept form, what I notice here are that these two equations are the same equation. They're exactly the same. If I rewrite them into slope-intercept form, I can see they are the same equation. So if I were to have a coordinate plane, and I'm asking you, okay, where do these two lines intersect? And here's line 1, and right on top of it is line 2. Yeah, you're going to get more than 1 point. So what's really happening here is because these are the same equation, they have infinitely many points where they intersect. Because ultimately these two lines lie on top of each other. So here's a point, 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 here's a point. These are all points where these two lines intersect, and there are an infinite number going forever to the left and forever to the right. So it's not all real numbers or all real solutions, because that's not a solution, and that's not a solution, and that's not a solution. So it's not every single coordinate that exists, but there are an infinite number of solutions that exist for these two lines because they lie directly on top of each other. So essentially, if you see that you are solving along, your variables are both gone, and you're left with this true statement here of 0 equals 0. This is telling you that you have the same line, They're the exact same equation and they lie on top of each other. So you can simply write that you have infinitely many solutions.